Alrighty, so we've got just a couple folks who are filtering in from the waiting room, but we'll go ahead and get going. So good morning, good afternoon, good evening. Welcome to this week's edition of Paleo Perks. My name is Elizabeth Seibert. I'm one of the Paleo Perks committee, and today it is my great pleasure to welcome Thamizharasan Sakthivel, who is at the Indian Institute of Science in India. And today he will be giving a talk entitled Plio-Pleistocene CO2 drawdown, driven by wildfire-induced terrestrial organic carbon burial. So just for those of you who haven't been to a Paleo Perks seminar before, or maybe who are coming back after a long time away, just a quick reminder of how these things work. So we have a brief welcome and announcements. That's what's happening now. And then Thamil will give a talk that'll be about 30 minutes, followed by a moderated question and answer period. After that, we welcome you to stick around for an informal tea time chat after. And if you have questions during the seminar, you can send them via the chat to the questions at Paleo Perks host, who is today is Neha. So just a wee little bit of housekeeping before we get running. Paleo Perks values participation of everyone who's interested in paleo sciences, and so we ask that you please remember to abide by our code of conduct during today's seminar. You shouldn't have gotten this link if you haven't seen our code of conduct, because you need to have signed up to get the link. But if you somehow slipped in here without having seen and signed that code of conduct, we ask that you please just go ahead and navigate over to the website and read our code of conduct for the day. We ask that throughout the seminar you remain muted for the duration, and if you have questions, you can send them via the chat to our questions at Paleo Perks host. We've actually got a couple of bandwidth things going on, so if you send a question to the questions at Paleo Perks host and you don't get an acknowledgement, send it via chat to me, and I will do my best to also catch it during the Q&A. If you decide that you want to verbally ask a question during the question and answer period after the seminar, you can hit that raise hand button and we will allow you to unmute. Any technical issues should go to the questions at Paleo Perks host as well. Just a couple other little things. We have closed captions built into Zoom. You can use that CC button you see on the bottom of your Zoom screen to show or hide them. And we are always looking for excellent early career researchers to feature in our series. So if you or any of your friends or any of your colleagues want to give us Paleo Perks seminar, please go ahead and nominate them in the forms that we've linked to in the chat. In addition, we have a weekly feedback form that we ask you to fill out if you're willing to. Just let us know who you are, and that lets us keep track of who's coming to these seminars. And then that's encouraged, optional, and you don't have to fill it out, but it really helps us keep track of things and make Paleo Perks better. And finally, speaking of making Paleo Perks better, we have some openings on the Paleo Perks Leadership Committee. So if you are excited about these seminars and you want to help this initiative to help support and grow the global community of early career researchers in paleo, we encourage you to apply. We've dropped the link to the committee application in the chat, and we'd love to hear from you and have you join us. So, all right, that's a lot of announcements today because we have this extra one. But enough about Paleo Perks. Let's talk about our speaker. All right, so Thamizharasan did his bachelor's and master's in applied geology at Pondicherry University in India, and actually held a visiting scholar position at the Karlsruhe Institute of Technology in Germany. And he's currently doing a PhD in geochemistry at the Indian Institute of Science. And so today we're going to hear all about his work in reconstructing paleo wildfires. All right, the floor is yours.
Yeah, so thanks for the wonderful introduction, Elizabeth. So let me share my screen. Please let me know whether my screen is right now it's a full screen.
It is not quite up yet, but we do see that you've started sharing, so I think we'll be there in a moment. Okay. All right, now I see your PowerPoint, but not your.
Okay, now it's a full screen, right? Yeah.
Yep. Now you're ready to go.
Yeah. So first of all, thanks for the invitation and opportunity to present in the Paleo Perks seminar. So myself, Thamizharasan Sakthivel. So it's tough to pronounce. You can call me Tamil. So I'm a final year PhD student from Indian Institute of Science. So today I'll be presenting one of the part of my PhD thesis here. So yeah, so my title might sound like ice cream is a good diet, but believe it or not, wildfire act as a good carbon management and long-term skills. So this presentation mostly deals on how the wildfire impacts on a terrestrial organic burial during Plio-Pleistocene transition and its impact on CO2 drawdown. So can you see my second screen?
We can no longer see your second slide.
So let me try stopping my video whether the screens are moving.
Okay. We were doing so well a minute ago. So
yep.
There we go.
So no, it's gone out. I hope my second screen is visible now.
Yes, it is.
So sorry for the interruption. Yeah. So why Pliocene? So Pliocene is Pliocene paleogeography is similar to the modern day, and most of the terrestrial and the marine species which were present in the Pliocene still present today. So here I'm showing it 4 plots. The top panel is the temperature, global temperature, and the bottom panel is the atmospheric CO2. So the right side panels are the temperature or climate record from industrialization, the future prediction in a different emission scenarios, and the left sides are the proxy-based temperature and the atmospheric CO2 reconstruction. If you take a mid-Pliocene, which is also known as mid-Pliocene warm period, it has some analogous in terms of temperature and the atmospheric CO2 with the contemporary climate condition as well as near future climate condition, which makes Pliocene as an important period to study. And this Pliocene warm period followed by a global cooling. And it's followed by 150 ppm drop down of CO2, which have an effect on a global cooling. The proposed, so the proposed mechanism for this global cooling and the decrease in atmospheric CO2 is to increase the continental erosion rate. So if you take the modern day example, so here this schematic figure shows how the erosion affects the carbon cycles. Here the units are in the flux units are in the million tons of carbon per annum. The upward fluxes are flux to the atmospheric or the source to the atmospheric carbon, and the downward flux are the sink of the carbon. If you take this sink only, the major sinks are coming from the burial of organic carbon, burial of carbonates, and the silicate weathering. So I'm mostly interested into organic carbon burial, which is a burial of both oceanic productivity based organic carbon as well as the terrestrial derived organic carbon. This presentation mostly focused on terrestrial organic carbon, which constitutes 23 to 47% of organic carbon burial modern day. And from now onwards, I will call the terrestrial organic carbon as a organic carbon biosphere. One of the major proposed hypotheses for the CO2 drawdown during this Plio-Pleistocene transition is increased glaciation over the high latitude and its associated global cooling and the climatic oscillations, like intersection glacial integration oscillations. So here in the right A panel, I'm giving the erosion rate, global erosion rate during past 4 million years, You can see it has increased from early Pliocene to Plio-Pleistocene, and followed by the B panel, which is the auctionized type of benthic formula, which gives the information about the global climate. It moves from the warm climate to the cold climate, from early Pliocene to Pleistocene, and followed by the atmospheric CO2 from both marine proxy, like a boron isotope in formula, or carbon isotope, stable carbon isotope of alkenones, and the continental proxy, like a stable carbon isotope of pedogenic carbonates from the continents. So all of them shows that the increased erosion rate during Plio-Pleistocene transition has a relationship with the global cooling or glaciation, and which are the relationship with the drop down of atmospheric CO2. So here I'm showing the spatial map plot from Herman et al. 2013. So here the circles are the location, and the colors indicates the ratio of the erosion rate during 2 to 0 million years by the 6 to 4 million years. The height and erosion rates mostly observed in the high latitude areas like Alaska, British Columbia, or Patagonia, and the low latitude high erosion rates are mostly associated in the high mountainous regions like Himalayas, Taiwan, like that. So here I'm choosing the fourth regime, which has both the erosion rate information and the wildfire related information. So here in this D, E, F, G panels are the D for Alaska, E for the British Columbia, and the F for the Tibet and the Himalaya, and D for the Papua New Guinea. The blue lines are showing the temporal extent of evidence of glaciation over these regions. And you can see the Alaska and British Columbia as a glaciation evidence since early Pliocene, whereas the Tibet and the Himalayas as evidence of glaciation from the mid-Pleistocene, and there was no evidence of glaciation from the Papua New Guinea. And interestingly, all these locations have increased. So the black ones are the wildfire proxy areas, it's a charcoal abundance or the pyrogenic carbon abundance. So you can see the increased wildfire activity during this Plio-Pleistocene transition. So yes, the glaciation associated cooling might have an impact on erosion. There, I'm most interested into the how this increased wildfire activity during Plio-Pleistocene transition have impact on global cooling and the burial of associated burial of organic carbon biosphere. So if you take a modern day observation related to the wildfire, so here I'm showing the Y panel time, and the x-axis is the carbon flux, plus is the sink, and minus is the source flux. So during wildfire, the carbon above the ground are emitted in the atmosphere in the form of CO2, or after the fire, even there are post-fire respiration and decomposition, which degenerates the organic carbon into the CO2. And also there is a sink, which is the production of pyrogenic carbon like charcoal, soot, or black carbon, which are relatively resistant for oxidative weathering compared to the original biomass carbon, which makes them as a sink of the carbon. So after so modern day, annually around 116 to 385 tetragram of carbon has been flux has been supplied to the ocean from the continent in terms of pyrogenic carbon. So the amount of carbon which has been released to the atmosphere is regenerated in terms of post-fire vegetation and making them as a net zero for a wildfire. And also there's a sink in terms of pyrogenic carbon. So wildfire not only make this sink as a pyrogenic, that along with the wildfire, there's another kind of vegetational another kind of a positive carbon sink, which is the vegetational shift. So wildfire are associated with, or grasslands or savannas are associated with the wildfire, both vice versa, due to their grassland resilient nature compared to the forest land. Grasslands holds 10 times more carbon below in the soil compared to the forest land due to its fine molly-salt soil compared to the coarse soils over the forest. So if we take an example, like if there is 1% rise in grassland over a particular area, which will increase the 9% increase in the total soil below the ground, which makes them the wildfires a net carbon sink in a long term, more than decadal time scale. So here I'm showing the how the wildfire can influence the erosion rate. So wildfire can influence the erosion rate through multiple factors. One is after wildfire, there will be loss of vegetation. After wildfire, there will be development of hydrophobic soil, means less water, but then soil, and the rock spallation, and post-fire storm, which transport these sediments and the associated organic matter from the continent to the ocean. Here, I'm showing the spatial map of average annual area of biomass burning between 1960 to 280. You can see the most of the biomass burning are over the South Asia, East Asia, Africa, and the Southern America. Interestingly, these regions are associated with the increased flux of organic carbon from the continent. So here I'm showing the flux with the units of 10 power 12 grams of carbon per annum. And you can see that most of the flux are coming from the South Asia, off the coast of Australia, and the South America, Brazil coast. So for present study, I have chosen the site from the Nicobar fan. So here the first panel is the site map. The red dot, the red circle is a steady site, and the rest of the circle I have used for another purpose. I'll tell that later. And the major sediment source for this site is coming from Indo-Myanmar range, and another one is the Andaman Nicobar accretion range, which is shown in the arrows. So, and here the right side panel is a mass accumulation rate, which is nothing but the dry bulk density multiplied by the sedimentation rate, which will give us the how much grams of sediment per centimeter square has been deposited over the time period. So the blue one is the Bengal fan, means mass accumulation rate, which is normalized to the modern day mass accumulation rate to get a perspective with respect to modern day, how much mass accumulation rate has changed during past 7 million years. And I have included the available IODP sites from the Bengal fan. And the purple, pink one is for the Andaman Sea, and the green one was the Nicobar fan. So modern day studies show that 70 to 85% of terrestrial organic carbon flux, which is coming from the continent, it's getting buried, or it's getting escaped from the bottom of the oxidation over the northern Indian Ocean, which is not the case in Amazon, where only the 10 to 20% of organic carbon is getting buried. So this burial is mostly due to the high sedimentation rate, which makes a quick burial of organic carbon in the ocean. So the high Plio-Pleistocene mass accumulation, the orange rectangle, which is our focus of the time period of the present study, which shows the high mass accumulation, which suggests during Plio-Pleistocene, the northern Indian Ocean have a high potential for organic carbon, terrestrial organic carbon preservation. So for regional sites like Nicobar fan, I have used two proxies for reconstructing wildfire. One is the stable nitrogen isotope of fixed ammonium in the interlayer of a clay. So ammonium in the site of the potassium in the clays. Another one is the well-established proxy, which is a pyrogenic carbon mass accumulation rate. To study the associated vegetation shift, I use the stable carbon isotope of organic carbon in the sediments. And to reconstruct the wildfire associated erosion rate, I have used the fixed ammonium abundance or fixed ammonium mass accumulation rate. And to get the regional organic carbon burial, I have used the organic carbon mass accumulation rate. To get the global perspective, I have compiled the 13 sites globally from Bengal fan. So these are the site locations from Bengal fan, Andaman Sea, Nicobar fan, South China Sea, and Amazon fan. These sites are selected based on certain criteria. One is they should have a Plio-Pleistocene record, sedimentary record. Number two, they should have organic carbon weight percentage data published, data whether it's coming from IODP, whether it's analyzed during IODP expedition or post-IODP expedition project. Second one is the age model is updated to geological time scale of 2012. The third one is availability of dry bulk density. Based on these four criteria, we have selected 13 sites and reconstructed global terrestrial organic biosphere barrier. For the case of wildfire, global perspective, we compile the multiple proxies, multiple available wildfire records from the multiple wildfire records worldwide. So here the symbols are specify different proxies starting from polyaromatic hydrocarbon to the pyogenic carbons. And I will discuss about the color later. So we have used around 16 sites for generating the global wildfire stock during Plio-Pleistocene. So let's jump into how the stable nitrogen isotope of fixed ammonium tells the story about the wildfire activity. During wildfire activity or during biomass burning, the molecules like carbon monoxide, NOx, and the VOC emitted to the atmosphere, and the photolysis process, it converts into tropospheric ozone. The major sink of the tropospheric ozone is plant uptake, but it will this uptake of the tropospheric ozone will decrease the productivity or the photosynthetic property of the plant. So here I'm in the right side, I'm showing the plot where the x-axis is the tropospheric ozone concentration, which suggests the wildfire frequency. Higher the tropospheric acid, more wildfire activity over the region. And the y-axis showing how the gross primary productivity deviates from the non-wildfire period. And here I'm showing for 3 different vegetation: temperate evergreen, C3 crops, and C4 photosynthetic herbs. You can see the anti-correlation between wildfire frequency and the gross primary productivity. Higher the wildfire frequency, lesser the plant productivity. So with this idea, we have used this stable nitrogen isotope of ammonium for reconstruction. So during wildfire or after wildfire, the amines in the soil degenerates, and in presence of microbes, it becomes ammonium. It doesn't mean nitrates won't form. Nitrates also form, but the amount of nitrates which are formed during this process is very less than how much amount of nitrate will deposit in the soil during the normal rainfall event. And due to high temperature in the soil, the nitrifying bacteria population is very low, which retards the nitrification process, ammonium to nitrate. So which makes post-wildfire soils are enriched in ammonium. This ammonium gets fixed into the interlayer sites of clay in position of potassium in case of illite. And also these ammoniums are utilized by the plants or the microbes after the post-fire event. The interesting thing is the isotopic discrimination, how much isotope fraction is during this process, or during the ammonification as well as the fixation of ammonium in the clay is negligible or 0, whereas this is, and the fractionation only solely depend on the microbial immobilization and plant assimilation process, which allows us to reconstruct how much is the ammonium utilization by the plant assimilation, which will tell us independently about the wildfire activity over the region. So here I'm showing the hypothetical curve for 2 events. One is high wildfire frequency event and a low wildfire frequency event. High wildfire frequency is like a minimum one wildfire event per year, and low frequency events like a minimum 1 wildfire event per 3 years. So here the stem density indicates how much amount of vegetation per unit area. So the drop in stem density records are coming from Pellegrini et al. 2021. And the top one is showing the 2 graphs. The dark blue is for low frequency event, and the orange is for high frequency event. And the y-axis is the top one is heavier delta, means the heavier stable nitrogen isotope of ammonium, and the bottom one is lighter stable nitrogen isotope of ammonium. At a given time, whether it's a n/3 or 2n/3 or n, the high wildfire frequency event will have a lighter nitrogen compared to the low frequency event because of less primary or grass primary productivity over the high frequency area, which retards the ammonium utilization. So here is my record from the Nicobar fan. So from now, means my y-axis is the age, and the x-axis is the different variable or different proxy record. Here the x-axis is the delta 15N of fixed ammonium, and the color panel is the fraction of ammonium utilized. This is estimated using the steady state model, assuming that the delta 15N of ammonium, final ammonium in the clay, it's the product of how much was the initial delta 15 of initial ammonium minus the fraction which was utilized taken by the plant. So we do know that the fractionation during the plant decimation, which is minus 9.4 per mil, and we reconstruct the fraction of ammonium utilized. Lower the fraction of ammonium utilized, more frequent wildfire activity. Higher the fraction of ammonium utilized, less frequent wildfire activity. So we do see high wildfire activity during Plio-Pleistocene transition compared to the early Pliocene. So this record also supported by the another fire proxy, which is pyogenic carbon mass accumulation rate. That also shows the more fire during Plio-Pleistocene. This I compared with the global wildfire stock. The global wildfire stock, I compared the multiple wildfire proxy record and the estimated Z score for each site. And here the turquoise color is showing the median line of the multi-proxy, and each with a time bin of 0.25 million years. And the shaded region is showing the 95 confidence interval. You can even see that the global wildfire also increased, highlights the prevalence of wildfire activity during Plio-Pleistocene. It's not only regional, it's also globally the Plio-Pleistocene wildfire has intensified. So here I'm showing the spatial map. So as I mentioned earlier, the symbol signifies the different proxy. The color signifies the ratio, which is the wildfire activity during Plio-Pleistocene transition by the wildfire activity during early Pliocene. And you can see the notable higher wildfire activity over the Asia and the Western Pacific during Plio-Pleistocene transition. So, yep. So wildfire acts as a carbon sequestration to majorly two processes. One is the production of pyogenic carbon like charcoal, another is the expansion of grassland. So wildfire promotes the grassland compared to the forest land due to their resilient nature, grassland resilient nature. So increase in wildfire activity increases the net carbon below the soil to promoting the grasslands over the region. So we have used the stable carbonized of organic matter. Here the D panel is the stable carbonized of organic matter. The absolute values are means the isotope values are given in the bottom x-axis. And I have estimated the fraction of carbon coming from the C4 biomass. For that, I have used the modern day stable carbon isotope of C3 trees and C4 grassland over the Indian subcontinent. The average value of C3 over Indian subcontinent minus 29 per mil, and C4 is minus 12 per mil. Using these two n numbers, we used the two component mixing model and calculated the fraction of carbon coming from the C4 biomass. You can see the two stages of C4 expansion. One is during early Pliocene, around 3.5 million years. Another is during Plio-Pleistocene, around 2.25 million years, so starting from 2.5. This Plio-Pleistocene associated with the high wildfire activity, which suggests similar to modern day during Plio-Pleistocene, also the wildfire facilitated C4 photosynthetic or grassland vegetation. Whereas the wildfire activity doesn't explain the early Pliocene vegetation. So what I did is I compared my record with all the available leaf wax records from the Bengal fan, which is the purple. Here the green one, the first panel is delta H, organic carbon from my site. I compared with the delta 13C of leaf wax from the Bengal fan IODP U1445, the purple one, and also compared with the continental record from the Himalayas. So you can see that all three locations shows the expansion, means heavier delta 13C, moves towards heavier delta 13C during the early Pliocene, which suggests the expansion of C4 vegetation. And the D panel shows the stable hydrogen isotope of leaf wax from the Bengal fan site, and the heavier value of delta D of leaf wax is indicating drier climate, and lighter value indicate wetter climate. So the temporal connection between expansion of C4 vegetation and the intensification of dry climate suggests the acidification is a major cause for the yearly Pliocene T4 expansion over the steady area. For the case of erosion, the important factor associated with wildfire erosion is development of hydrophobic soil. We have seen how the isotope value of fixed ammonium changes, but the fixation process is driven by the hydrophobicity of soil. Higher the hydrophobicity of soil, higher the fixation of ammonium in the clay. Because lower the hydrophobicity soil condition, like a high amount of water in the soil, which increases the interlayer distance in the clay, which leads to diffusion of ammonium from the clay intersite to the soil solution. Therefore, higher the hydrophobicity soil will have a higher fixed ammonium. So I have used this idea to reconstruct the erosion rate. So here the dark blue panel, the first panel, which is the fixed ammonium of more from my side, which shows 3 times increase during Plio-Pleistocene transition compared to early Pliocene, which suggests a 3.2 times increase in erosion rate. And this increase in erosion rate consistent with the independent proxy of erosion rate from Central Asia, like and the center on the yellow one, which is based on 10 beryllium-based erosion rate from Central Asia. Also, the exposure ages from the Himalayan foreland sediment. So all signifies the erosion rate has been increased at least regionally during the Plio-Pleistocene transition, which is associated with a high wildfire activity. This temporal element suggests wildfire played a significant role in continental erosion. I'm not telling only the wildfire played erosion, along with the global cooling and the oscillation of intensification of glacial event, wildfire also played an important role increasing the continental erosion or Plio-Pleistocene transition. Yeah, so to get the regional global perspective of associated terrestrial organic carbon biosphere burial, we compile, as I already told, we compile 13 sites. And here the right side shows the organic carbon flux over the different oceanic region, Bengal fan, Nicobar fan, South China Sea, and Amazon fan, as well as Andaman Sea, with the respective color. So if you see the global flux, it has increased 1.7 times during Plio-Pleistocene transition compared to the early Pliocene. But if you also if you see regionally over the Nicobar fan, the green one is Nicobar fan, which shows 2.7 times. And we can see this notable increase in organic carbon burial, not only in the Bengal fan, also we can see it in the, not only in the Nicobar fan, also we can see it in the Bengal fan, South China Sea, and Andaman Sea. You can see it in the blue one, which is Bengal fan, Andaman Sea is the pink one. Whereas it's not evident in the Amazon fan, the purple one. It's mostly maybe due to the less sedimentation rate over the Amazon fan, which exposes the organic carbon to the bottom water oxygen and allows the bottom water oxidation process. So to get the significant correlation, so here the A panel shows the correlation between global organic carbon biosphere burial versus the global wildfire stock, and B panel is relationship between atmospheric CO2 and global wildfire stock, and C panel is atmospheric CO2 and the global organic carbon burial. Each data point is a 0.25 million year time bin, and the colors, the color shades are indicating different times during Plio-Pleistocene. And you can see the positive correlation between global wildfire stock and the global organic carbon burial, which suggests this wildfire played a significant role in transporting and burying the organic carbon in the ocean. And the negative correlation between atmospheric CO2 and the global wildfire stock and the global organic carbon burial suggests wildfire played a significant role, contributing significant role in CO2 drawdown during Plio-Pleistocene boundary or transition. So the takeaway message is that here I'm showing a small schematic plot. The steady X, Y1, Y2 are the fluxes during early Pliocene. Here I'm showing with respect to early Pliocene how the Plio-Pleistocene fluxes has increased, or changes. The sediment flux over the Nicobar fan has increased 3.2 times compared to yearly Pliocene. The global organic burial has increased 7 times, sorry, and Nicobar burial increased 2.3 times. So in this present slide, I discuss only the wildfire impact on terrestrial organic burial. Wildfire also supplied nutrients like dissolved iron and the phosphorus to the ocean, which facilitated phytoplankton productivity. And that is my future plan, to study how the Plio-Pleistocene wildfire impacted the marine organic carbon or marine productivity. Thanks for listening to my presentation. Yeah, I'm looking forward for the questions or suggestions, any comments. Thank you.
All right. Thank you so much for that seminar, and I'm so glad that we got you back after that brief bandwidth issue. So that
sorry
was,
for that issue. Yeah.
It happens, and I'm glad that we got you back. Thank you to everyone for joining us today, and we have a bunch of questions in the queue. So we'll just go ahead and get those going. So the first one is actually in the chat already. This is from Sender, and Sender is asking, how localized is the organic carbon burial preservation caused due to wildfires? Is it more globalized? And then could the shift in the position of the IPCC from Pliocene to the present contribute further to the organic carbon burial?
Okay, so if I understand correctly, so currently, the most of the record which I compiled is from the tropical region, where I could get the so my compilation is based on multiple factors, like updated age model or the record available for Plio-Pleistocene and the organic carbon and the proxy. There are public whether the organic. I checked whether these organic carbons are significantly coming from the terrestrial regime or the marine regime. Whether their publication, there are already published records which suggest this are significant from the terrestrial. So regarding ITCZ transition, that I can address once I have the organic carbon burial record from any high latitude or mid latitude region at the moment.
Cool. All right, thank you. So just a quick reminder to everybody who's here, if you have questions, you can put them in the chat to the questions at Paleo-Perks post, and we will read them out. And the next question is a little bit related to this one. Is it possible to differentiate between the frequency of fires and the size of fires from your proxies?
Yeah, nice question. So we were going around this bush for more than a year. So yes, at last we have come up with the conclusion that the delta, stable nitrogen isotope of ammonium, suggesting the frequency of fire, whereas the size of the fire, still I'm thinking, because I don't think so the charcoal or the rest of the pyrogenic carbon will give us any information about whether it's the intensity or the frequency. At least right now, we are a little bit confident. We're confident that nitrogen isotope provides the information about the frequency. Yeah, size of the fire, we are looking for a better proxy at the moment.
Cool. All right, so the next one is also from Sender and asks, do wildfires, particularly wildfire frequency, affect C3, C4, and CAM-based plants equally? And if no, is there a particular reason for that bias?
Yes, so C4 or the grasslands can recover from the wildfire more quicker than the bigger trees. So there's a problem. So there's a problem, like we mostly assume that grasslands are mostly C4 grasslands. Of course, C3 grasslands are also there, but modern day we do see that wildfire expand both C3 and C4 grassland. But the more evidence is like if you ask statistically, the more evidence are from the C4 expansion grassland. Okay, regarding camp, I have no idea about regarding camp, how the wildfire affect the camp vegetation. And this the reason is that the grasslands are more expand during the wildfire activity because of its few vegetation regeneration compared to the bigger trees or forests.
Great. So we actually have a question that just got popped in the chat, so I'll read that one out before I go to our next one in our queue. That question is, how does the wildfire affect the paleo biodiversity in the source region? And I'm actually, because this question is very similar to the next one in the queue, I'm going to add that one, which says, are there changes in pollen or other indications of vegetation changes in these sediment cores? So I think they're very, very related. They're the same question in a lot of ways.
Thank you. So when you ask you, there are changes in the pollen records from the Sunda, which is near to our Nicobar fan site, which also shows the grassland expansion during Plio-Pleistocene transition. And regarding paleo-biodiversity, if you see more than the vegetation, of course, there are changes in the increase in grasser population over the Indian subcontinent, which is associated with the Plio-Pleistocene wildfire activity.
Great, thank you. Okay, so we have just a couple more questions. So if you also have burning questions, I'm sorry, I didn't mean to do that. If you also have questions, feel free to put them in the chat, either directly or to the questions that Paleo Perks hosts. And I will read these last couple of questions as we go. So this question is a little bit more taphonomic based. It says, how much is the preservation of biogenic nitrogen impacted by sediment mass accumulation rates? Have you ever tried plotting the ratio of nitrogen isotopes against sediment MAR, and do they have a correlation, for example?
Yeah, so in my case, I separated one, I removed the biogenic nitrogen reacting with the potassium bromine and potassium hydroxide solution, so there's no biogenic nitrogen, and this is only the fixed nitrogen, fixed ammonium in the clay. Regarding this relationship with mass accumulation rate, I got it. So we did a Sadler, we checked the Sadler effect. So the relationship between mass accumulation rate and the ammonium weight percentage, organic carbon weight percentage, is R square is always mostly less than 0.2, which shows it's not driven by the Sadler effect or the sedimentation rate.
Okay, all right, so this is our last question unless anyone else gets one in between now and when we're done. So this question asks, does the frequency of wildfire and type of grassland vegetation have any association with the terrain, given that you're considering or comparing samples from the Himalayas, IODP, and the Nicobar Islands?
Interesting. So is the it might have terrain, yes. So if you take a Himalayas, if you take an altitude wise, it's there's a changes in vegetation which is driven by the altitude associated mean climate change. Yes, there is a change in effect, but the sediment source with I made a comparison in 3 different locations. One is from Nicobar fan, one is from the IODP site of Bengal fan, and there is from the Himalayan foreland. The sediment, if you see in a broad context, the sediment source are derived from the Himalayan forelands. Whether it's Nicobar fan, it's coming from Indo-Burma range, which is a part of Himalayan foreland, and the Bengal fan, it's also coming from that. So yes, I have to look into terms of terrain, whether the different terrains have any effect, frequency, wildfire frequency have effect on grassland or not. I have to look into that deeply.
Great. Well, thank you so much. This has been a really, really fantastic seminar. So we'd like to go ahead and do our little outro. So thank you, Thamizharasan, for a fantastic seminar. It was really, really interesting. And I know I'm a sucker for paleo wildfire. Thank you to everyone who's joined us today for today's Paleo Perks seminar. And we'd like to remind you to please, if you are able to fill out our weekly feedback survey. We also have links for speaker nominations and to join the Paleo Perks Committee in the chat. And we'd like to invite you back next week when we're going to have something completely different, when Pablo Mila of the University of Bristol in the UK will be giving a paleontological talk titled Studying the Transition Between Micro and Macroevolution from a Morphological Perspective. There's one last little plug for joining the Paleo Perks Committee. We want this to continue, and so we'd love to have some early career folks come join us. And then if you stuck around this far, up next you'll know is tea time with our speaker. This is again a very informal conversation in a relaxed setting. And our question of the week is, which natural disaster would you most not want to be near? So think about that during our 2-minute break. So now it's time for our break before tea time. So get up, have a drink of water. If you have pets, bring them back, and hopefully we'll have a nice conversation. So we'll see you all in 2 minutes.